Let's look at properties of solutions, mixtures of solutes into solvents. And let's look first at a saturated solution of a solid, say in water, H2O. This is the process of saturating a solution. As the solid dissolves, concentration of the solute molecules or ions will increase. But, as we can see in these next couple of slides, the solute molecules can then precipitate onto the crystal. And when those rates of solvation and precipitation are the same, then we have an equilibrium established in a closed system, and you have a saturated solution. No more of the solid than is in solution already can dissolve, but there's still a solution process and a precipitation process going on. So, the process of crystallization, then, is the opposite of the solution solvation process. When the rate of dissolving equals the rate of crystallization, the two processes are in dynamic equilibrium, the solution is saturated. No net change in concentration of solute will be occurring. So, for example, sodium chloride reacts or dissolves in water to form aqueous sodium ions and aqueous chloride ions. Now, let's look at this time since mixing versus concentration of solution diagram. As you can see, as the solid dissolves, more of it is dissolving than is crystallizing. But when you get to a point here where this levels off, what's happening is the rate of dissolving is equal to the rate of precipitation or crystallization. And that's going to continue at the same concentration of solution until, for instance, we change the temperature. The solubility of this solid is the concentration of a saturated solution. And it's usually measured either in grams per 100 milliliters or in moles per liter. For instance, the solubility of sodium chloride is 357 grams per liter. This varies with temperature. This is at 0 degrees Celsius, and it goes up a little as the temperature goes up. You can make solutions with lower concentrations. These would be called unsaturated solutions. Now, some solutions can be made with an excess of solute above the solution concentration that is we call saturated. This is usually made by taking a solution and putting as much as you can in at an elevated temperature, then cooling it. If there's no crystals left, there's no site available for beginning the crystallization. There's no seed to start crystallization. If we do add a crystal or bump the supersaturated solution, then crystallization will proceed until you have a saturated solution, and the crystals will fall to the bottom of the container. Such processes are almost always exothermic. This is a nice diagram showing an unsaturated solution where more solute can dissolve, a saturated solution which is going to have some solid in it, and a supersaturated solution with crystals that are growing larger because more of the solute is going to come out of the solution. Now, irregular crystals in a saturated solution can be regularized with time. This shows that there's a dynamic equilibrium going on, and it also shows that the more regular a crystal is, the lower in total energy it is. There is an energy improvement, reduction, when the solute molecules come together in a regular crystal. Now, whether and how something dissolves in another depends on the temperature and on the nature of the interaction between the solute and the solvent. And let's look at gases. Gas solubility increases with molecular mass. Why is that? Well, it implies an involvement of dispersion forces in the solution process. That is, the London dispersion forces, as you know, are instantaneous dipoles that are set up between molecular substances, between molecules. Gas solubility increases with molecular mass, and an increasing size of the solute molecule increases the London dispersion forces available because it increases the number of ways a dipole can form. Therefore, the solvent will have more attraction for the solute. But if we add chlorine to the list of the gases, it goes way up to 0.102 molar. Compare that with the solubilities here of these gases. We surmise that chlorine must be reacting with the water to be absorbed by it so well, and this vastly increases the solubility of the chlorine in water. Here is the reaction, chlorine reacting with water to form hypochlorous acid and hydrochloric acid. Chlorine water is a valuable mild oxidizer, and you can see the structural formulas here. Now, are liquids miscible or mixable? Well, polar liquids mix in polar solvents. For instance, acetone mixes with water, and it's miscible in all proportions. You can see the acetone's polar nature and water's polar nature. Polar liquids do not mix with nonpolar substances. Benzene is nonpolar, water is polar. They're not miscible in any proportion. You can see the benzene structure here and is obviously nonpolar, C6H6, and the polar nature of the water, one of the most polar molecules there would be. Slightly polar organic molecules will mix with water, but maybe not in all proportions like acetone. For instance, diethyl ketone is not miscible in all proportions. Small alcohols are miscible 100% with water, but the large ones are only partially miscible with water. And here is 1-heptanol, which, as you know, has 7 carbons. It is slightly soluble in water, but not in all proportions. So predict whether each of these substances is more likely to dissolve in nonpolar carbon tetrachloride than in water. So we have heptane, sodium hydrogen carbonate, hydrogen chloride, iodine. Answer: nonpolar carbon tetrachloride dissolves nonpolar iodine and heptane. Polar water dissolves the cyanic substance sodium hydrogen carbonate, and the hydrochloric acid results from the HCl. What's the effect of pressure on gas solubility? Well, if the solubilities of solids and liquids are not significantly impacted by pressure changes, what about gases? Well, all gases are more soluble in any solvent at high pressure than at low pressure. This is true whatever the solvent is. This is true whatever the gas is. Why? Well, let's look at a diagram here. At any given pressure, the gas above the solution here and in the solution would be at equilibrium. The pressure would remain constant. But suppose the pressure is changed. We'll push the cylinder in. Kinetic theory predicts that increased pressure will increase the rate of collision of the gas molecules with the solution. This increased collision rate will increase the rate of gases entering the solution phase until a new equilibrium is formed. The new equilibrium at higher pressure will find more gas molecules in the solution, and that means it doesn't depend on the gas, it doesn't depend on the solvent. We can measure this phenomenon and we find that there is a direct proportionality between the gas pressure and the solubility of the gas in the solvent. The solubility is directly proportional to the partial pressure of the gas above it. This relationship is expressed as Henry's law, which you will see here. There is a constant. When you multiply that by the pressure of the gas, you will get the concentration of the gas in the saturated solution. For AP exam practice, you might want to explain this phenomenon using Le Chatelier's principle. So, question: why does soda pop explode from its container when you shake it before opening it? Answer: Shaking it increases the kinetic energy of the carbon dioxide and the liquid so that the gas is much less soluble and rushes out of the solution. That is, you have established a new equilibrium constant. Here's a sample exercise involving Henry's law for you to do. Turn off the video and then check back your answer. Henry's law is expressed in this way. So the concentration of the carbon dioxide is equal to the constant times 4 atmospheres, which is 1.2 times 10 to the negative 1 molar. So solubility as a function of temperature is a thermodynamic question. Most solids require energy to dissolve in water. Most solids are more soluble in higher temperature water. Most gases, however, are less soluble in higher temperature water. That's why fish die when the water gets too warm. So for further research, you may want to research the various methods that deep sea divers and scuba divers use to avoid what we might call death by Henry's law.